In this video, we are going to talk about what are called piecewise functions. Sometimes a function is defined using different equations on different parts of its domain. For example, the absolute value function, f of x equals the absolute value of x, is actually defined by using two equations. F of x is equal to x when x is greater than or equal to 0, and f of x is equal to the opposite of x when x is less than 0, or it's a negative number. So we can express both of these equations in one expression known as a piecewise function, which we show below. So f of x equals the absolute value of x, which is equal to either x when x is greater than or equal to 0, or opposite x if x is less than 0. Just to drive this point home, I'd like to graph both of these functions. So we have y equals x, and we have y equals negative x. Okay? I'm going to just copy and paste these very quickly. And let's think about what this piecewise function is saying. And again, this is y equals negative x, and this is y equals positive x, the red line. So the way that our absolute value sign or function works when we think of it as a piece function is this. We are going to use the function, we're going to use the graph y equals x, or f of x equals x, when x is greater than or equal to 0. So that means we will use this graph whenever x is equal to 0 or greater than 0. So we're going to use this part right here. And so what we're really going to do is we're going to not use it for this other part, so I'm going to just get rid of that. And we're going to use f of x equals negative x whenever x is less than 0. So that would be for this point here. We're using this. And we can cross out, we're not going to use that. We're only using that function for the negative values of x, not for the positive values. So we kind of got rid of part of it. And notice when we put this together, we end up with something that looks like the graph of the absolute value function, which we did in an earlier video. And in fact, let's go back to Desmos and just show you that that is the case. If I graph on top of that y equals the absolute value of x, right, you see that we have this new green line that is, again, made up of two different parts of the graphs right here. And so I get rid of those parts, and that's what I'm left with. When a function is defined by different equations on different parts of its domain, it is called a piecewise defined functions. And often we'll just say a piecewise function. So let's go ahead. And we'll do a couple things for three different graphs, three different piecewise functions. So first, we'll find the domain of that function. We're going to locate any intercepts, and we're going to graph the function, and then based on the graph, find the range of the function. When we're finding the domain, it's really easiest to just look at this part right here. So I'm going to find my domain, and notice that either we're going to have in the top, it's all x that are not equal to 0. That's at the very top. So if x is not equal to 0, that means it's any other value of x. besides 0. So that's all real numbers except for 0. But then down here we have, or x could be equal to 0. This tells me that for number 32, x, the domain is just going to be all real numbers. Before I locate the intercepts, to be honest, I like to graph the function first. So let's graph this function. All right. So I'm going to draw my axes. And so it's 3 times x, except when x is equal to 0. So 3. So I'm going to graph 3 of x for every point except x equals 0. What would that look like? Well, 3x is really just a graph that goes like 3 times 1 would be 3. So that would go here. 3 times 2 would be 6. So that would go here. 3 times 3 would be 9. So that would go here. 3 times -1 would be -3. And so on and so forth. We can find a couple points. Now, these are not the only points on this graph, because obviously all the points in between, for example, 1 and 2, are going to be included on this graph. And so what I really want to do right here, and I'm actually going to do this in red just so it's a little easier to see, is I'm going to really, if it was just 3x, it would be a straight line going through the origin. But I don't want to include that origin, so I'm going to put an open circle right there. And I'm going to draw my graph of y equals 3x. And the only difference in my graph is I put an open circle where x is equal to 0. Because remember, it is only equal to 3x in all the points except for where x is equal to 0. What happens when x is equal to 0? When x is equal to 0, that means that f of x is equal to 4. And so I'm going to put a point when x is equal to 0, y is equal to 4. I just put an extra point right there. And that is my domain. I'm sorry, that is the graph of this function. Are there any intercepts? Does my graph touch either of the axes? Well, it doesn't hit the x-axis because there's a hole there, right? That's an open circle right there. It actually doesn't touch x. The y value is never equal to 0, right? It never touches the x-axis. However, it does touch the y-axis. So we could say that there is no x-intercept and the y-intercept is 0, 4. Or you can also say the y-intercept is equal to 4, right? Often y-intercept can be expressed as a point or as the y value. So y-intercept is 0, 4, or just 4. Either one of those answers would be fine. We already graphed the function. Let's find what the range of the function is. So the range of the function is interesting. You have to be careful. It almost looks like it's from -infinity to infinity, but it doesn't hit every y value. It is missing one y value. My range is all y except for 0. And the way we express this in interval notation would be You go from negative infinity to 0, and you put that together with 0 to positive infinity. That's all the numbers less than 0 and all the numbers greater than 0, but not including 0. And we just put those together. All right, so that's our first example. All right, let's do another example. I'm going to just copy and paste this. And in fact, maybe I'll just go it off to the side. No, I think it's fine. All right. Let's start with number 35. Again, when I'm doing my domain, I'm just going to look at this. So this is all the numbers in between negative 2 and 1. Then I also have 1, and I have all the numbers bigger than 1. Putting this all together, so the smallest possible number is negative 2, and then it goes up to 1. It includes 1, and then it goes to infinity after 1. So really, this is going to be all the numbers starting at negative 2, and it includes negative 2, so I'll do a square bracket, and it really goes all the way up to infinity, right? If I was going to graph this again, just to remind us, just so we can see, this would be from negative 2 to 1. That would be this first part. And at first we would have a hole here, right? That's just this part. But then when we look at the next part, x is equal to 1, we fill in that hole. And then x is greater than 1, that's everything to the right of that. And so as we can see, my domain is all the numbers between negative 2 and infinity. All right, let's graph this. And I'm going to graph it maybe over here. Let's see. So this will be that was part A, and we'll do part C next. Right there is fine. All right, and let's start with negative 2. We'll do this part first. X plus 3, y equals x plus 3, that's going to be a linear equation, right? It's going to be a straight line. So I'm just going to find from negative 2 to 1 what that straight line looks like. So I'm going to plug in negative 2. If I plug in negative 2, hold on one second. Negative 2 plus 3 is positive 1. So I know this point is going to be on the line. And if I plug in 1, that would go all the way up to 4. One thing that's important, though, is that I'm not including this point on my graph yet. So I'm going to do an open circle from here to here, and I just connect from here to here. So that is the part of the graph of x plus 3 in between negative 2 and 1. What happens when x is equal to 1? Well, that means y is equal to 5. So I fill in a dot right there at 5, right above it. What happens after that? Well, when x is greater than 1, then it is, we're going to have negative x plus 2. And I'm actually going to plug in 1 first. So when I plug in 1 into this, I get negative 1 plus 2, which would be positive 1. But again, I'm not including this, so I am going to graph it, but I'm going to graph it as an open circle here as well. So that would be 1, 1. And then what if I do the next number? What comes after 1 is 2. Negative 2 plus 2 is 0. So that goes here. If I plug in 3, negative 3 plus 2 is negative 1. If I do -4, or I plug in 4, I get -4 plus 2, which is -2, and you can kind of see what's going to happen. Now this keeps going in that same direction until infinity. And so that is my graph of this function. All right. Are there any intercepts? Does it cross the x-axis? I would say yes. It crosses the x-axis at 2, 0. So the x-intercept is at 2, 0. Or you could just say the x-intercept is equal to 2. Does it cross the y-axis? I would say yes. It crosses the y-axis right here, which is 0, 3. So the y-intercept is 0, 3, or you could just say the y-intercept is equal to 3. All right, based on this graph, what is the range? This is going to be a little bit potentially complicated. I would say we kind of have 3 different parts. I'm just trying to think how to put this together. What's the smallest possible y value? The smallest y value, well, as you can see right here, it's just going to keep going to -infinity. So that means that it will be, the smallest possible value is -infinity. And then it will keep every number starting at -infinity all the way up to y equals 1 will be on that part of the line. And y will equal to 1 right here, and it'll keep going all the way up until y equals about this, y equals 4. Right? So with these 2 parts that I highlighted, we have all the numbers in between -infinity and +4. But notice that 4 is an open circle, and that's at the point 1, 4. So we don't want to include 4 in our range. Now that's not every single y value. There's one more y value, which is this point right here, which again is 1, 5. And so we're going to put this together with just the 0.5, and we're just going to put this in, what do you call it? Set notation. Probably have it like that. Most likely that would be the best way to express it. I think you can make the argument you could maybe, I don't know if this is appropriate or not, but all the numbers in between 5 and 5, including 5, I don't think that's probably the best way to put that. I think the one above it is better. All right, so we're done with that one. Let's do one more. All right. First, let's start with the domain of the function. We have 2 different parts. Either x is less than 0 or x is greater than or equal to 0. Putting that together, just like in number 1, we see that we are really dealing with all possible numbers. We have all the negative numbers, and then 0 and all the positive numbers. So our domain is from -infinity to infinity. Now let's try to graph this. And I'm going to try to actually make my graph a little bit bigger. So I'm going to just say that's 1, 2, 3, 4, 5, etc. Just so it's a little easier to read, so it's not so tiny. But let me start by marking my axes. All right, let's give this a shot. All right, when x is greater than 0, or when x is less than 0, then we do 1 divided by x. And so 1 divided by -1, for example, would be right here. 1 divided by -2, that's going to be 1/2. 1/2. 1 divided by -3, that's going to be -1/3. And 1 divided by 1 divided by -1/2 will actually be -2, so that goes here. And it might be helpful just to graph on your graphing calculator, what does this look like? But it should end up looking something like this. Or if you are familiar with the parent function 1 over x, it'll look something like that. In fact, let's just go to Desmo so you guys can see it. Okay, and so as we see, this is my left-hand side. For all x values less than 0, that would be this left-hand part of this graph. What about when x is greater than or equal to 0? In fact, let's just graph this one too. Y is equal to the cube root of x, and again, the way I enter this in my calculator is I do x raised to the 1/3. Okay, so it's going to be just this red part, or I'm sorry, it'll be this purple part, except only when x is greater than or equal to 3. So I found a couple points. There's 0, 0. There's 1, 1. And I guess what would be another, and I guess there would be 8, 2. Would be another point that's on there. And so we have 0, 0. If I plug in 0, the cube root of 0 is 0. If I plug in 1, the cube root of 1 is 1. And if I plug in 8, the cube root of 8 is 2. And again, I'm just going to label all these so you guys can see them. All right, so I'm going to plot those points starting at 0, 0. Then I have 1, 1. And then I have 8, 2. So I only have 1, 2, 3, 4, 5. This will be 6, 7, and let me just get rid of this, 8. So 8 will be for 2, so that goes right there. And those are my 3 points. And it looks like this. Okay? So that is my graph. And let's go ahead and locate any intercepts. Does it cross the x-axis? It actually crosses both the x-axis and the y-axis at the origin. So the x-intercept is 0, 0, or you could just say 0. The y-intercept is at 0, 0. All right, what's the range of this function? Definitely goes on this part right here. This range is really from -infinity all the way up to 0, right? It never quite touches 0. The graph of 1 over x is asymptotic with the x-axis, so it gets closer and closer to the x-axis as you go further and further to the left, but it never touches it, so that's that part. But what's the blue part? What's that range going to be? Well, it really starts at 0, and even though it's not growing very quickly, if you keep going, this will just keep on getting higher and higher and higher. And if you think about it, you can find the cube root of any number you want, no matter how big it is. You can always find a number that when I multiply it by itself 3 times, it will add up to that number, or it will multiply it, it will equal that number. So this will be from 0 to infinity. So notice we have everything from negative infinity to 0, not including 0, but then we include 0 and go all the way to positive infinity. So our range ends up being all the numbers in between negative infinity and infinity, including 0, because we have 0 as an output right there. All right, and so that is the range of this function, and we are done with piecewise functions. I hope that this video was helpful, and we will see you in the next video.